Hello everyone, this video is about the lab exam 2. Now the task was to design the function pCritical that takes in a GSS, a transfer function, and returns KC and TC. Now here this K is basically the p-type controller, the critical gain value, and then also the frequency or the period of this critical gain value. Now this function can be used in order to tune a Ziegler-Nichols PID controller, because the requisites there are that you take a p-type controller, take GSS, form the closed loop, and look at the j-omega crossings. And this is about that. Now, since we need a p-type controller and the system and the closed loop, let's start coding that. Now, since we have a transfer function already given here as an argument, it is still the best to try to be safe and define your symbolic s variable. You can obtain also the variable from the symbolic expression, but to be simple, let's define sims s. Now we have GSS. What we need is basically the following. We need to define our p-type controller, sims k, and let's define it real because we are working with a p-type controller, which is a static gain, and that should be real. It's not a complex number. Now, since we have GSS and k, let's define our closed loop transfer function, k times GSS, and then 1 plus k times GSS. Once we've done that, we need the characteristic polynomial, because the p-type controller will be tuned so that we have a j-omega crossing. So therefore, we need to, you can also maybe write down PZS and PCS and then use num then from TSS. But I don't really need PZS, and if I don't really want to define another variable that I'm not going to use, instead of having an unused variable, what you can do is you can just use a tilde, therefore. It will extract the numerator and denominator, but the numerator will be thrown away, because we only need the denominator in this case. So it really doesn't matter. You can use tilde, you can use PZS, whatever you want. So then we use num then to obtain PCS here. And at this point, we need to actually remember the fact that if we have PCS, let me write it in mathematical notation. If we have PCS, and if we have this equation PCS equals 0, any s equals something, let's say sigma plus j omega, on the s domain, if it's a solution, it'll satisfy line 7. This is really important. If you have a real root, for example, s equals -2 and j omega is 0, then if you plug in this value into PCS, you'll get equals 0 if it's satisfying that. And therefore you might also get the corresponding k value, because PCS is an expression which has k in it, which is unknown at this point, which is a symbolic variable. So you can use this method in order to determine if a root can be satisfied with a p-type controller. So therefore we're looking for not a real value, not a complex value. We are looking for a pure imaginary part, j omega, because that's the point where we lose sigma, and e to the power of minus sigma t is the damping part of our solution. If that's not there, then we have a sine wave. Now, you might need to check out the inverse Laplace table for that. But we need to look for s equals j omega. If we plug in s equals j omega, and then we get the critical part, or marginally stable part. Here, the marginally stable closed loop is asked here. So therefore, if we plug in s equals j omega, we can do that by, let's define p omega, something like that. We can do that by using subs, which is substitute. Instead of using s at this point, I want to use 1i times omega. Now we didn't define omega, but omega is the frequency where this happens. Therefore, let's also define omega. And we also know that omega by definition should be real and positive. So therefore, we have sims s, sims k, we've used the closed loop transfer function, we've extracted the characteristic polynomial, we've defined an omega value, and used that omega in order to substitute s equals j omega. S equals j omega. So at this point, we might go ahead and display this p omega in order to see what it looks like. So therefore, I've also prepared a test script, and this is important. We are coding a function. Therefore, there is this function module, which you are trying to code. And then there will be also a script that calls your function. Most of the time we use functions right on. Therefore, we might skip this part, but it is important for lab exams especially, because I'm collecting your functions only, not your scripts. Therefore, you should code your function like this. It doesn't have any input. It doesn't have any output here. Some of you have attached some code on top of here, maybe like this, in order to test out your function. It's not a good idea, because you then also submit this whole file here, and if I use a script that tries to call this, it can't, because the first line is a Matlab script and then there's a function embedded into the script, so it's getting confusing for Matlab. Therefore, I did manually fix them by deleting these parts or commenting them out. So you should separate your script from your function when you're trying to solve in a lab exam. Therefore, I've done this here. So just follow this guideline, you'll be okay. Now we have a test script here. So therefore, let's define also sims s, because we are, if I'm coding it right, sims s. There we go. We need to define GSS. Now here we have a memory space for this script, and then this function has its local memory space. Therefore, if I define sims s here, it doesn't affect the local one, or the local space here does not know about sims s. That's the beauty of a function. Therefore, I might copy sims s here, but other than that, I'm just going to define my transfer function. And then I can go ahead and copy this first line here up to this point, like this, and we're good to go. Now, since I've used a disp here, I should be good to go. So I've forgotten to open up Matlab. Let me just quickly do that. So now, yeah, we are going to display this, and here, since we've plugged in a complex number or a pure imaginary part, I suspect that p omega should be a complex valued expression depending on omega and k. So that's really important to note. So there we go. Now we have Matlab. So let's call this test script here. And there we go. So this is an important error. Now, some of you have coded maybe the function, but most of you have forgotten that you have to assign KC and TC. And as you can see, we didn't even define them. So we didn't assign them. And Matlab complains that KC and maybe others, also TC, was not assigned during the call to p-critical. Now, you might argue that you can delete this part and then call p-critical, and that's not a problem. But in my script and in the task here, it is shown that you should use it like this. Because if I call it like this, and I'm going to call this as given here, then I'm going to look for KC and TC. If they are matching, then you're going to be okay. And if not, then unfortunately, yeah. So therefore, you might call on your own using p critical, etc. But if you want to test this out, you should use it like the notation given here. Therefore, for now, let's just assign 0 and 0, but this is not a good strategy. Just for now, for debugging purposes, I'm going to do this. And let's run it again. And as you can see, since I've plugged in s equals j omega into 1 divided by s plus 1 plus k, or s plus 1 plus k, I get this result here. Now, what now? Well, basically, I've talked about the fact that I should equate it to 0 if p omega is equal to 0. Let me get rid of this. So if p omega is equal to 0, then this root satisfies this polynomial. Therefore, but also note that we have a complex number. So if this is equal to 0, this means that the real part that I'm getting here should be equal to 0, and the imaginary part should also be equal to 0. Therefore, what we can do is we can form our problem, which is get the real part of p omega equated to 0, get the imaginary part of p omega equated to 0. There we go. So let's maybe also display the problem here. There we go. Now k plus 1 should be equal to 0, and omega should be equal to 0. Now immediately you can see that omega can be equal to 0, and k is equal to minus 1. So this corresponds to a j omega crossing where we are not crossing any frequency, we are crossing the origin. And this happens most of the time in the negative root locus, which I can see here, because k is equal to negative 1. So I'm on the negative root locus. In terms of root locus, I'm just commenting on this. I'm interpreting this result, and I can see that on the negative root locus we have a crossing at the origin, which makes sense because we have only one pole, which goes to the left for the positive root locus and goes to the right for the negative root locus, and at a certain point it will cross through the origin because it's on the real axis. Therefore, we will also get a negative k value. So, and once I have this, I can go ahead and solve it using Matlab. And let's extract k val, convert it into double. Now it is also important, if you have a numerical result, try to store it numerically, because the symbolic engine does work with double values if they're only numeric values. But some other toolboxes, since this is a function, might not work with the symbolic numbers. So therefore it's always a good idea to convert this into numerical data here. So let's display k val and omega val in order to see if we're there. There we go. We can see that k is minus 1 and omega is 0. Now the task here does not ask for omega directly, but it wants us to calculate the frequency or the period of this. So therefore what we can do is we can just go ahead and use the fact that omega is equal to 2 times pi times f, or 2 times pi divided by this. So yeah, since we'll use this here. Now this is an important point. If we have a first order transfer function like this, then we can go ahead and directly use t equals 2 times pi divided by omega. So this is pi. Am I correct? I guess so. So it is possible, and let me assign tc to that, and let me assign kc to kval at this point. So now we're good. But you should also keep in mind that, by the way, it's omega val, because this is the numerical value. Now you should keep in mind that there's no guarantee that omega val will be a scalar. And also I didn't check for omega val's negative values because that doesn't make sense and I should eliminate them. And you can see that here we have no third data here because one of them is a real crossing, one of them is basically a j omega crossing, but that j omega crossing has only one value in it. So I should maybe eliminate the negative omega values and yeah. Therefore, we are missing some stuff here. The example has a third order system, so therefore we should also keep that in mind. But before that, I can see that omega val is not guaranteed to be a scalar value. Therefore, if you're not really good with the dot operator, you can use a for loop and take individual elements and inverse them. But if you're good with them, what you do is, if you want to divide element by element, you just include the dot here, and then dot divide or dot slash here gives you the effect that we want, because it'll take individual elements, inverse them, and put it in an array, if omega val is an array. So, and let me show you that this will hopefully work for for order 1. So here we have KC and TC. Now we can see that -1 and infinity is the result that we're looking for. Let's also maybe try this version where we have KC and TC. It seems to be working because we have only one element here. But let me leave it like this and update the function here. So let me take this here. So that's basically one case 1. Let me also look for a different transfer function, case 2. Now here, let's copy this part here. We've defined the third order example, and then we have KC and TC. Now let me also maybe should be display. Let's call them KC and TC, or maybe just get rid of the semicolon here. So there we go. And by the way, I've not included the dot here. Now, some of you might have solved it like this. You can see that we have -6, 34, and 34, whereas the answer does not include a second one. And we have also TC, which looks a little bit interesting, because we have infinity and 2.22, but here we have 0, -2.2, and 0. So something went wrong here. And that place is actually one of the places is this one here. You should not divide 2pi divide by this. You should use dot divide by. And if you want to be really safe, you might also include this here. So 2pi, and then divide individually to omega bar. Let's see what the change is. For once, we have TC equals 0, and we have a negative TC and a positive one. But now the issue is that we have duplication here in terms of 34. And that duplication comes from the fact that we have negative omega val. So let me just also display omega val here. Now we can see here omega val is 0, -1, and infinity, because 1 divided by 0 gives you infinity. Which means, by the way, that if you have 0 frequency, you have no period. So, yeah. And here we have omega 0, -2, and 2. Which means that we should eliminate this, because this doesn't make sense. Negative omega is not a solution at all. And therefore we get this weird thing here. Therefore, let's get the indices. Index equals omega val. Now this is again important. If you have a first order system, then you might cross the origin. Or in this third order system, we again have the origin included. in order to be able to include the origin, instead of having greater than 0, we have greater than or equal to 0. This is important. So, or another maybe safer way would be to look for the negative ones, eliminate them, but I'm going to stick with this. So it can be 0 because we can use the origin, which might not be for the Ziegler-Nichols method because it uses the j omega crossing that omega, but we should provide this. Therefore, we'll use index positive n equal to 0 and omega val and k val should be eliminated like that. So k val index omega val index. So it is also important to note that at this point, if you use omega val instead of index, instead of defining the index as a separate one, and if you mess up the order, you can see that here we have already eliminated them, but then we check again, but k-val did not eliminate its unnecessary values. At this point, if I run this, I'll see that omega val has, for example, 2 values in it, but k-val has a length of 3. So most of the time I use an extra variable for this in order to be able to save. So I declare a variable that has all the indices that are necessary. At this point you can also mess up the order, it's not really important. And you eliminate based on the index value. Because if you use this 2 times, then you're checking it 2 times, which is not really how it's done. So at this point we have also individual division here, and kc is equal to k-val. Now let's look at that. There we go. Now we have -1 and infinity for the first order case, and then we have -6, 34, infinity, and 2.22. So, yeah, this is basically the solution of this, and I have tried to talk about the possible problems, one of them being to not eliminate the omega vals that are not really suitable by definition, or by eliminating them with the wrong code, because if you use this and this, let me fix it, instead of defining index and messing up the order, you might get into trouble. That might be a problem. Other than that, using greater than or equal to 0 is important, because you might say we might have missed this, but you can't, because we have -6 and infinity, which is already an origin. So this is an origin crossing. This is not j omega crossing. So since this is a third order transfer function, it has one origin crossing on the negative root locus, and it has a pair crossing on the positive root locus. So it sometimes might help by checking the positive and negative root locuses of this transfer function, and then you can see which points are important to us. And by the way, we give the widest range of solutions here, and we leave the rest to the user. If you use this, you get all the candidate points, and then you're on your own. You should decide which one suits you, because if you have a 5th order transfer function, then you will get multiple j omega crossings and maybe also origin crossings. Therefore you should be careful. And we, as pre-critical the function, don't give any warranties. We just give you the positive or equal to 0 omega val solutions, and then we're done. So that's basically it. Hope that this video was helpful, and that you've maybe spotted your possible mistakes. And yeah, I've also seen that some other solution algorithms were tried to execute it, but yeah, this is the safest way. And I remember that I've talked about this in somewhere in the laboratory at some point. Therefore, the lab exams, by definition, are basically towards the laboratory. So if you pay attention, you might have catch this point. If not, it is troubling, because you have to come up on your own, that you might use the characteristic polynomial. You might have to plug in s equals j omega, and then there are some possible values that you might be interested in, and some of them are not really suiting the definition, etc., etc. So therefore, this is called lab exam, the laboratory exam, because it is towards the laboratory, and it tries to somehow evaluate your laboratory knowledge. Yeah. So that's it. See you in another video.